Good evening, everyone. I'm Apurva, and this is week 10 for Games and Information. Um, Before we start this week's tutorial, we are going to take a quick recap of things we have done so far because they come in handy eventually. So, in the last tutorial, we talked about in the last tutorial we talked about mixed strategies versus behavioral strategies. Uh, can you tell me what is the difference between the two?
Mixed strategy defined on pure strategies,
Uh,
and behavioral is defined
so,
individual information like
okay, you're correct with the idea, but you have to use the right terms. So, the correct terms is in mixed strategies, you're randomizing over pure strategies, or you're putting probability distribution on the set of pure strategies. So, okay, the correct word is randomization or probability distribution. In case of behavioral strategies, we're randomizing again, but we are doing it at each information set. Okay, then we also talked about is there an equivalence between them? Mixed strategy and behavioral strategies. So, for this, there were two theorems by Kuhn that came up. If I have to say it in a very loose terms, then it basically said that if players have perfect recall, we can either use mixed strategies or behavioral strategies. We'd be at least able to get the same um, expected utility out of that. Then there is a kind of an equivalence between mixed and behavioral strategies. This is the summary of both of those theorems put together. One, okay, I didn't mean to say if perfect player, if each player has perfect recall, then there is a equivalence between mixed and behavioral strategies. We talked about this and we also saw how to convert a given behavioral strategy to a mixed strategy and a given behavioral strategy to a mixed strategy. So, like, we were able to go from one to another. So, today we are going to talk about a different kind of game. All of this was on games where we had either perfect information or we had imperfect information. But the players knew the payoff matrix, so to say, or the players knew what was being played, what was happening in the game. They may not know the exact path that is being taken by the players, but they knew which game they were in. The examples that we're going to talk about today are the scenarios where players do not even know what part of the game they are in. So these are called incomplete information games. Uh, So, before I go into the technical points and how it is defined and the formal definitions and so on, let's take a few examples. So, I would prefer giving examples in words. Okay. Consider this example. This is an example where there are two players. Player 1 is a seller and player 2 is a buyer. Both of them are trying to sell or buy, respectively, an indivisible item. They'll both have some notion as to what should be the price of that item. So this is a bargaining game. So the two are they're going to negotiate. But let's say this negotiation is happening in one round. So seller says a price, buyer says a price, if there is an order, or they both say their price and then decide what happens, whether the buyer buys it or not. Those rules are fine, but in this scenario, we wouldn't know, like player 2 wouldn't know what value player 1 has assigned to the item. Because he doesn't know the value of the item, he will not be able to tell what is the actual, player 2 will not be able to tell what is the actual value of the utilities that he'll get at the end. So the utilities, so for example, if player 1's decided value is S1 and player 2's is S2, then see, this is coming up in utility function in some form. I will come to this notation aram se, but the point is, player 1's idea would be to sell it at the highest possible price, but the buyer's objective would be to try and buy it at the lowest possible price. But they have to sort of have almost an agreement before they actually buy it. If there's too much of a difference in what they're saying, the buyer may choose not to buy. Okay, so in games where the utility function is affected by something that is not known to the players, so in both of these scenarios, either we are talking about utility of player 1 or utility of player 2, they're both affected by the S1 S2 values, and these S1 S2 values are not known to the players beforehand. In fact, these S1 S2 values are the ones that they are trying to optimize over, like find the best value that makes sense. That's the whole point of bargaining. Okay, so in situations where player may have certain undefined criteria that are sort of hidden, he knows it, but the other players won't know that. Those are the kind of games where the utility functions are also affected by it. Those are the kind of games where there is a lack of information to players in terms of this thing called a type, or that the players could be of different types. That's a typo. I meant types. On the other hand, when we were talking about imperfect information games, even if we made those trees, so if we made a tree like this, let's say this is player 1, this is player 2, even if there was some information set here, making it in a rough manner, but if all of these, if both of these nodes were in the same information set that they can't be distinguished, player 2 doesn't know the action taken by the first player, but player 2 does know what are these payoff values. He knows what game is being played, he knows what is being done, he knows that both the players are optimizing, either maximizing, minimizing, or whatever, but that is very clear. But there are games where this may not be known, where we'll come to it, the tree form will be slightly different. There will be an added something that brings in uncertainty into the problem. And these types of games are called incomplete information games. So the key word here is, there is some information that player themselves know, but the other players don't know. And that private information is what is typically called as a type. And this is the main difference between an incomplete information game and an imperfect information game. Okay, so let's talk about it in a bit more formal way so that we can understand the examples better. So let's say there are a set of players, so this denotes, N denotes the set of players, Ti denotes the type of player Pi, or rather this is the set of all types of that player. So what I'm saying is, Pi will know which particular type he is. This is very similar to what we saw in the example in the very beginning, when we were talking about common knowledge and information, where there was one player who was colorblind, and it was known to everybody. And there was another player, P2, who could be colorblind or he could be not colorblind. This thing, player 2 having two distinct states, is what is being referred to as types here, and the set of all of these types is denoted by capital TI here. This is specifically for player 2. So now in such a situation, so I think this one was Paul, this one was John. I don't recall the names, but maybe you can verify if you want. Anyways, so Paul knows whether he's colorblind or not, but John doesn't know that. John knows that he himself is colorblind. In fact, John is colorblind is known to everybody, that's common knowledge. But his state is not common knowledge. Because his state is not known to everybody, this type of information, meaning if the game proceeds where both of them are colorblind, they'll behave in a very different way. On the other hand, if John is colorblind but Paul is not colorblind, and he knows that he's not colorblind, and he also knows that John doesn't know this part, the game will behave in a very different way. So there is an asymmetry in information, and that asymmetry is at the level of some sort of a private information for the agents. And we can say that these states are chosen by nature at random. So either type 1 is chosen or type 2 is chosen, or if there are more players, so whatever, for each of them some type is chosen. So what nature would do is he would either go for a state like this where both of them are colorblind, or he would say, okay, John is colorblind but Paul is not. That's the state he chooses, and hence there'll be some sort of a probability distribution on top of that. Now, since we have some probability distributions coming up here, these probability distributions are on the type profile. So there would be some sort of probability distribution of this kind. So say there are n players, so some sort of probability distribution of this kind. Now, if we are in a situation where this is common prior, this is something that's known, the probability, this overall probability is known to everybody. That's one scenario. Another could be where they don't have complete information here also. Okay, so let's continue. So now here, since we have introduction of probabilities at the level of type, we will also have something called as belief. Each player would have some notion of what part of the game they are in. So that particular belief can be in two different forms. One is called ex ante belief, that is before the types are realized, meaning belief after nature has chosen the profile, the type profile, and given it to the agents, given it to the players. At this level, if we're looking at a belief, then that means each player PI knows nothing about his own type. So right now he'll have a by default belief about everybody else. So that is before any realization. That's called ex ante belief. Other possibility is, because now this is after he got TI. So after he got to see the state TI, he says, okay, now that I know what is my type, based on that, maybe I can make a better guess, I can have a better probability on what is the probability of getting any particular profile for the all other players. So T minus I refers to type of all the other players, the realized type of all the other players. Okay, is the notation clear? So far, this T, capital T or small t is the new introduction here, and this refers to types. We are saying that there is a probability distribution on top of that is given by nature, and on that each player can have a belief, as in So for example, if I look at this particular probability, this is the belief of player I about the information of all the other players, all the other minus I players, or the type of all the other players. This is the scenario before the types are realized, meaning PI doesn't have his own type available to him. So that's why there's no conditional here. On the other hand, as soon as he knows his own type, he can condition on that and find a probability belief of minus i's information given his own information. So these are all beliefs of player PI. That's the way we have written it about other players. Okay, so now next thing that comes up is how is action going to be selected. Okay, so one simple way is in each type of the game there would be some set of actions available to each player. So from that an action is selected. So this kind of an action that is getting selected is a pure strategy. It's a pure strategy, or it's what we can in extensive form as we call as action. And this capital UITI is a set of actions of PI in that type. See, now we are using the information of type and then saying what is an action. Point is, in different games or different parts, different types of games, we may have different set of actions available. So if you recall, the examples that Sir gave was, let's say there is a security officer, and that's, let's say, player 1, and player 2 is people who are entering the airport. In player 2 there are multiple variations to that person. That person could either be some sort of a threat to security, or it could be just an innocent person. So now if this security person is supposed to identify which type it is, only then he'll be able to move forward. So first he's going to identify the type of the other player, so he'll have some sort of a belief on that, which is what we talked about here, meaning he knows his own type. So the security person will have some sort of idea as to what to look for to identify which type it is, or something of that sort. Then based on which scenario it is, based on what belief he has and which side he's leaning on, he will then decide what to do with it. If the other player is actually a threat, his actions will not be the same as his actions available if the other player is an innocent traveler. If it's an innocent traveler, he'll just check the basic documents and let them pass. But if it's a threat, then after checking the documents, getting suspicious for whatever reason, they may have other set of protocols, other set of actions to take. That is why these actions are now, or these set of actions are based on type for each player. Now, since that is the case, since now everything is dependent on type or which particular portion of the game we are in, that means even the utility will be based on the type. So it will depend on type and whatever action is being taken for all the players, so as a profile. So let's say this is the cost for player PI, where the type profile is capital T, meaning it's T1 to Tn for all the players, and action profile is U to UN for all the players. Now, just like earlier, we can have a few different versions of strategies. One standard one would be to take a type and come up with what to play for that particular type. So this kind of a strategy is just a pure strategy. It's looking at a type value, so it's looking at which part of the game we are in, and then just after whatever careful evaluation or looking at the outcome of the game or the solution of the game, just saying, okay, this is what is my strategy, this is what I'm going to play. So now this depends
What
on type. Yeah.
One question. What is the difference between capital TI and small TI over here?
Capital TI is the set of all the types for player T. Now from here we'll get one realized value for that player TI. So using
Okay.
that, whatever set of actions he has access to, from those he'll choose an action. That's what it means. So this is the
Oh,
realized value of that.
okay.
Yeah. So this one is a pure strategy. On the other hand, we can also have behavioral strategy. Now, recall when we talked about randomization last time also, when we talked about behavioral strategies in games with imperfect information, the behavioral strategy was conditional on information, the information set. Or we didn't use the word conditional, we just said that the behavioral strategy is defined at each information set, which means once we have reached that information set, then we are deciding what to do. That may be our plan beforehand, but the plan is only if we reach that, then this is what is to be done. Otherwise, we don't need to worry about it. Similarly, here, behavioral strategy could be with respect to the type. So again, it's a probability distribution on this set. The actions available in that type for player PI. Okay, so
I get the part of the behavioral strategy thing, but just one more thing, like regarding my previous question only. So a player can have multiple types also.
yes,
Since you're saying.
yes.
Do you have an example just to?
I'm coming to examples.
Okay.
Okay, yeah. Okay, we're starting with this example. Okay, before I take an example like this, let me take a easier to understand example. Take this one. I'll explain what each of these things mean. So there are two players. There's player 1 and there's player 2. Now, in this situation, this is a situation where player 1 and player 2 are supposed to decide whether to fight or not fight or yield. So in one situation, player 2 is strong, in another, player 2 is weak. Now, whether player 2 is strong or weak, player 2 himself would know that. So in other words, you could say that for T2, the type set, the set of all types for player 2 would be strong or weak. So maybe I can represent it this way. This refers to strong and this refers to weak. So this is and player 1 has no such consideration. In fact, this outer box basically says that player 1 cannot distinguish between these two. For him, these two are the same things, as in these two parts of the game are indistinguishable to him, and he'll not be able to tell which part of the game he's in, whether he's in this part of the game or whether he's in this part of the game. Basically, he doesn't know whether the other player is strong or weak, and hence for him,
Right.
type would just be, so T1 would just be whatever his own type. So there are no variations to it, so we can just call it I1. Now see, to be able to write these payoff matrices, just like we said earlier, we need the full type, the type profile. So I need what is realized, whether it is this one. Here there's only one option. From here, whichever is realized. And we need whatever action we are talking about, and we'll talk about all the players. So with that in mind, this is the type profile. Maybe we can call it T1 and this is T2. So these are the two types for the game, overall game itself. If we are to talk about it with respect to the two players, player 2 can be either strong or weak, meaning you can think of player 2 being chosen from a set. Who gets chosen is something nobody knows, but somebody gets randomly chosen from a group, in that group there are two options: either that person is strong or that person is weak. And once that person is chosen, player 1 still doesn't know who got chosen. Only once the match actually starts, he'll know, okay, this person is weak or strong. Or in this game scenario, he'll decide whether to even fight or not. Okay, so this is a cleaner example of what a type means. Or in the example that we've been saying so far, the security example with a threat versus an innocent traveler. So that threat and innocent traveler, that together can be called as one player. Let's say that's player 2, and player 1 is the security guard who's trying to identify which of the two types is it, and based on that take their action.
Makes sense. Yeah.
Okay, so this is one example. Let's look at a more abstract example now. Okay, so this is the other example that we are given. In fact, this was the example in class also. So here what is being said is, so for player 1, he has two types. So whatever those two types are, player 1 will know which it is. On the other hand, player 2 has only one type, and well, he wouldn't be able to distinguish between these two. So now the type profiles are these two, this and this, and then there's a probability given on top of both of them. Right? These probabilities you can think of as being given by nature. With some probability, nature is choosing whether the type profile is this or this, meaning it's telling you which part of the game you're going into. And here, whether here or here, player 1, because he knows which his own type is, he would have known what nature has chosen and given it to him, so he'll know the realized value. Player 2 has only his own realized value, so he will not be able to distinguish between them, meaning player 1 will be able to tell which part of the game he is in, or he'll be able to see the matrix, the payoff matrix, but P2 will not be in this particular example. Okay, next let's say the actions are following. Sorry. Player 1 plays up or down, player 2 plays left or right, and this is for all the types. Player 1 has only one type, this is small t1, the small t2 refers to these two values. So now we are asking, can we represent this game in that extensive form game that we have talked about, or can this be formulated in the same way as we had imperfect games? So let's try doing that. So there is nature, so let's call it player 0. Player 0 decides which part of the game it is, so either it goes in this case, this is one type of the game, this is the other, then it's some player's turn. Okay, and this is happening with probability half. Now we need to figure out which player should be playing first. So let's think about it this way. If player 2 plays first, he will have his action. Player 2 will be playing what? LR, okay. But what did we say? Player 2 is someone who will not be able to distinguish between these two scenarios. So for player 2, these two should be in one information set. We are arguing if player 2 were to play before, is that a feasible version or not? So okay, this much is still working. Let's continue from here. Now after player 2, let's say player 1 plays. Now what should I do about the information sets?
So player 1 would for player 1 the first two will be in one information set and the second two will be in another.
So you're saying like this?
Yeah, because you can distinguish between I1 and I2.
Is this doing exactly what the main thing was doing? So what we basically needed was player 2 should know which type of the game he's in, whether he's here or here. And he does know like whether nature played this action or this action, even if we have drawn it this way. Similarly, this could have been drawn in the opposite way. So I1, we could have changed the order of play for the two players. So player 1 played first and he had UD. Okay, yeah. Should I be putting an information set here or not?
No.
No, correct.
No.
Perfect, correct. Why not? Because player 2 knows which type he's in. Player 1
one.
knows his type, meaning there is no information set here. This is valid as it is. Now we can go to the next player and then see how to draw that. Now let's say player 2 played, and what should be hidden to him, what should be visible to him?
He has only one information set.
Player 2 has only
He
one
has only
information. Correct. So for him, all of these things should be together. Reason is there are two things happening. One, this was more evident here. Player 1 and player 2 both don't know the actions taken by the other players because we are dealing with simultaneous move game or static game. Okay, that's why we've put all of these together. Another thing that's happening is player 2 cannot distinguish whether he's in this part of the game or this part of the game. That's why all these 4 nodes at the bottom should be in one information set. Okay, so now if suppose this was UD, okay, now if instead of it being a static game, if it was a dynamic game where what are we asking? Okay, if the dynamic game is where P2 knows the action of P1, so we can draw in the same order. So here P1 either takes U or he takes action D. If P2 knows this action, he should still not be able to distinguish between whether he's here or here. He can tell whether action U is taken or D is taken, so he can distinguish between these two. But he should not be able to still distinguish between these two nodes. That is why this would give an information set like this. And similarly for D also. Okay, now let's try and see how will our arguments change for this way of drawing the extensive form game. So let's start with player 0. Same types. Player 2 plays first. Okay. Player 2 knows the action, so by default it is saying player 1 would have played before. So the second way is not meaningful whatsoever. The order is by default given from the dynamic game itself, so we can't do anything about it.
Makes sense.
Yeah. So what we have done is we have tried to understand these games with types, or what we are calling as incomplete information games, in a manner very similar to imperfect games, with the addition that there may be a 0 player that gives the types with some probability. Okay, here the probability was given to us as equal for both of them. That might not be the case in general. Okay, now let's take a few examples. So for example, this one, we have already identified the types. What else is there in this example? If I want to draw the extensive form for this, how would I go about doing this? Again, we have two players, player 1 and player 2. Player 2 has types, player 1 doesn't have types, meaning player 2 would be able to know what these are. So let's say we start with 0. Player 2 plays first, so we don't need to put an information set here. And then player 1 plays. Now player 1 can't distinguish between any of them, and since we are given these as normal form, so we can assume that what they're referring to is a static version of the game. So this is going to be the rough diagram for this game.
Right.
Yep.
Yep.
Okay, now let's look at a few more examples to get a hold of this, and then we'll talk about other concepts related to games with incomplete information. Okay, so this is another example. So in this example, there are two teams which are playing against each other. When the toss is done, at that point the teams sort of make a decision how they are going to play, whether they are going to aim to win or they're going to aim to draw, and that changes their, not their actions, but at least their strategy, and hence their payoffs also. So in this game, can you tell me what is the type of each player and how can we think about this game, at least based on things that we have seen so far? So okay, let's say player 1 is this one, so maybe that's referring to Argentina, so let's just call it player 1. So for player 1, the types are either to aim to win or to aim to draw. Exactly the same way, player 2 also has those same two types. Means, unlike before where the game was the game was either in this block or this block, now there are actually going to be 4 blocks because each player has different variations.
Right.
So we could try drawing that, but that's a very unnecessary process to do. 1 minute. Is there anything else that we need to look at in this example? No, not really. Okay, so at each type, each player has actually the same actions available. The actions are whether to attack or to defend. So for player 2, it is again attack and defend for each of its type.
So we have the profiles as WW, WD, and all these 4. So why the 2 wins? Does that mean there are 2 games or something?
No,
Like
no,
when you
there are
can
overall 4 games, or
four.
there are 4
Okay,
parts of the
okay.
game. Which one actually happens is given by nature. So, if we were to actually try and think about it more carefully, we're not given the probabilities, but never mind. We could still be like, okay, there is nature, the player 0, who chooses which of the 4 profiles is to be played, whether it is both are aiming to win, or win and
Okay.
draw and win, and both are trying to draw. And then beyond this, you're making the game tree for each of those profiles. So here you'll just make the simultaneous game for this particular type. That's it.
Right.
So now that the way we are talking about this game has changed from how we were talking about games with perfect information, we'll have to rethink about what is the meaning of Nash equilibria in these. In fact, we have to talk about strategies also more carefully. So all of that will come to. Okay, so I'll leave this part if you do want to draw this. Okay, this is another game. I'm not going to actually solve this one, but this is actually a very nice game. So think of a problem of bargaining. So there's a seller and there's a buyer. The main part of this game is both the seller and the buyer are going to say the value, the price that they want the item for at the same time. Let's say whatever the item is indivisible. They'll both have some sort of a price in mind. That player 1 might be like, okay, I would want to sell it for X amount. Player 2 would have some other amount. Maybe we can call those amounts as S1, S2 for player 1 and player 2 respectively. So the game is defined in the following way. So there are 2 players. So that's the set of players. They both have a type. Now type here refers to the value. One second. S and theta are different things. Okay, so each player knows what the object is worth to himself. Okay, so this is their own. Where is it? Where is theta? The worth of any particular object is defined by the players themselves. That is represented by these thetas. The small theta values refer to each of these realizations. For in this particular example, there are 100 of them. And then we are given that each player has a belief on them, and the belief is a uniform belief. So belief means, so for example, this one is player 1's belief about theta of player 2. That's why theta 1 is in condition and theta 2 is what you're looking at. So this is the probability that theta 2 is a particular value given theta 1 is a particular value. So each player is trying to have a belief about what the other might be thinking, and these are uniform beliefs, so there's not much to it. And then on top of that, okay. So now the different part is this one. They will each announce a bid. Bid meaning a value that they'll say. Now that's the distinction in this game. Theta was the type that they knew, but that's not the one they're announcing. What they're announcing would be some value S. Either it's S1 or S2. Now the payoff for each player will depend on whether they actually decide to buy or sell or not. That's okay. But here, for player 1 to know whether the product will be sold or not depends on what was the bid given by the other player. And he wouldn't know that bid given by the other player unless that happens. So even the payoff is affected by the whole situation. So in that sense, this is a game with way too many types, so I'm not gonna bother drawing them. That's 10 to the power 4 choices for nature to take from, and each will have the same probability 1 by 10 to the power 4. Okay, so
So
this
the
is
probabilities are 1 by 100, right? Like as mentioned that for the others. And what is S? Can you just repeat once?
yeah, so S are the bids. S1 or S2 are the bids by each player. So by player 1 and player 2 respectively.
Okay. So there are just two players. Okay.
Yeah. For the time being, we're saying there are two players. Each player
Okay.
has
Right.
some notion of how valuable the prize is. Based on
Okay.
that notion, they'll make a bid. Whether they'll be like, okay, if they value it a lot, then they'll probably bid it for a higher price if it's the buyer who's bidding first.
Yeah.
Because they would want to acquire it. It's that kind of an idea, right? If the buyer is not that keen, if the price is already is not that much, he'll go for a lower bid. If he still gets it, he'll be happy with it. If he doesn't get it, it doesn't matter. So that's roughly the idea that is captured in how the utility is defined.
Okay. And how did you get 1 by 10 to the power 4?
Okay, so what I'm actually saying, that 10 to the power 4 is the probability of theta 1, theta 2. Not the joint, the joint probability actually. So these two are since the same, the joint will just be product of these.
Okay.
If they were actually, so if this actually depended on theta 1 and if this depended on theta 2, you'd have to use Bayes rule and then try and figure it out. But here, because that's not the case, it's fairly straightforward.
Okay.
Yeah. Okay, so by the
And
way,
here it's not dependent. How are we sure about that? That theta 1 is not dependent on theta 2 in this case?
it's given to be 1 by 100 for each theta value.
Okay.
They've said it. Where is the statement? Yeah, here.
Right.
With the same probability. This is a very simple game. You could have more interesting versions. So if this is the kind of game that you found interesting, then maybe looking at these type of games would also be interesting. So auctions can be modeled as Bayesian games. So there are a few versions in auctions also. I think first bid auction, again some second bid auction and something like that. As a personal preference, I don't like these examples, but these are illustrative. So I'm not going to go through any examples of this kind, but these are very standard. If you are interested, you could look up examples related to auction and they'll show you the whole process. They'll actually solve for Nash equilibria in those examples also.
Got it.
Yeah. Okay, so let's continue now. So now let's talk about the payoff. So if we were just dealing with a simple scenario, if we were dealing with no randomization or anything, we were dealing with pure strategies, then where is it? Okay, fine. If we were dealing with just pure strategies, then the utility would just be, for each player, the utility would just be ji of t comma u. The order doesn't matter. Where u refers to the action, rather the action profile, meaning it's all the players, and t refers to the type profile for all the players. But this is for pure strategy. That is fine. It's the expected probability that is more interesting. Reason being, we said earlier that belief can be of two different types. Either we can have a belief before the type is realized, and we can have a belief after the type is realized. So that comes into picture. So we can have expected utility in a few different forms. So this is the first version where we are saying for each type, for each player, there will be some behavioral strategy that gives us an action or a set of actions to choose from. So and we take a product of all of those behavioral strategies and multiply that by the expected utility for that
Of course.
pure strategy, and this we need to
Yeah.
do for all the actions for that type for all players. So it's pretty much all of it. Behavioral would basically assign a probability value to each of these boxes, any of these boxes, yeah. So behavioral would assign some probability for this, some for this. So we just have to take all of those probabilities multiplied by this and sort of go on throughout the whole thing.
Yeah, so basically for a specific type profile, we are calculating the average or the expected value, considering all the actions.
Yeah. So now the thing here is no player will actually know the profile. This is something the observer can know, that okay, these are all the different profiles, all the different type profiles, and hence there can be these behavioral strategies, but no player will actually know which one is happening. They'll know only the one that is happening. They'll not know all the other ones. That's the whole point of calling it an incomplete information game. That means players will actually not see these payoffs, and if they don't see these payoffs, defining equilibria with this notion of utility will not be the right way to go about it. So rather we go for these two types of utilities. Okay, so this second one,
Okay.
which is generally used for pure Nash equilibria itself, as in Nash defining Nash equilibria, is if we are just taking the expected utility and not expected utility, if we are taking this JB this
Expected
utility
for
and
all
then
type profiles. Right?
yeah, then we're just taking the expectation with respect to all type profiles, because no player will know particular profiles, but they'll at least have this distribution for all the type profiles, because that part is common knowledge.
Right.
So this he can calculate. So this is the expected payoff before he actually got to know his own profile, because we have not taken any conditionals.
So, like the probability distribution over types would be of common knowledge, but this cost value, that is something that how will the player know? This GI.
So what he's doing is he's fixing a T profile.
Mm-hmm.
So if he has fixed a T profile, so maybe he has fixed the T profile to be this one for the time being. And then here he's saying, okay, with this is happening with some probability, that probability is actually alpha. But then he's just saying that, okay, I will have a behavioral strategy that gives me some probability distribution on all four of these.
Okay.
So I'll just go through them. So whichever player I'm talking about, player 1 or player 2.
So he will have this kind of information also, basically. The payoff values as well.
This will be available. This whole payoff thing is available. It's just that players don't know. So, for example, in this example, player 1 doesn't know whether the actual thing is going to be this or this. Because for him, both of these will be in one information set. So he can't distinguish. But player 2 knows exactly which one it is.
Right.
So where were we? Okay. So this is one scenario. The other scenario is after each player has received their type. So now they won't bother with this overall probability. Instead, they'll take a conditional with respect to their own whatever realization that they've seen. they're assuming that all the other realizations have some sort of correlation between them, and hence if they are conditioning on theirs, this might be more informative. So same thing, the only thing fixed over here is we are no longer taking the expectation with respect to ti. We're still taking for all the other t minus I, but not this one. Ti is fixed, that's something that's realized. So with that fixed, we know now which one box to go for, not all of them. Once we have fixed that, we're just taking the belief probabilities, or these Bayesian probabilities. These we can calculate if we are given the priors, these common priors, or if not, typically the conditionals are by default given.
Okay.
Okay, so I was planning to take an example, but maybe it's better if we take the example once we start solving for equilibrias only. Right now might not help enough. Okay, so now let's talk about defining equilibria. So there can be two different versions. Both of these are valid. The only difference is this is before knowing the type, this is after knowing the type. And obviously you can see that if you if you take an expectation with respect to ti for this utility, you'll ultimately be getting this. So they do have a relation between them. Okay, so Nash equilibria says that a behavioral strategy profile is Nash if fixing the behavioral strategy for all the other players, unilateral deviation does not help for all BI,
Right.
for all players. This is Bayesian. This other case is, the only thing that has changed is we are conditioning on TI. And this conditioning needs to hold for all types. If this conditioning holds, then whatever B we got, this B1 star, is part of the Nash profile. Bayesian Nash profile.
Right.
Okay. So one more thing over here is that we can think of these incomplete information games in something called as agent form. Agent form is basically saying, starting from nature, there are these different variations possible, and each variations there are players who are playing, and so on. So we can say that each type of every player can be thought of as a distinct agent. So they call this as agent. Let's say in the original version of the game, what we are calling as players, those players have types. For each of those players, for each of the types of each of those players, what we get is a kind of agents. And then we can say ki, okay, all of the rest of the arguments are as it is. So now this is the number of players or agents for that matter.
So TI was the total, capital TI was the total number of types, right? Which is why we
For
are
each
saying
player.
that for each player. Okay, for each player.
Yeah, for each player. So then you can just sum over for all the players. Okay, then for each player, the way you will define actions would be just taking an action from the available actions in that TI. So each player means we are already referring to one of those TIs. So for the player TI or the agent TI, the action is just this, something picked from UI of TI. In that case, the expected utility for any particular ti. So now you're fixing a type. Now that we've fixed the type, we are in short saying that there is kind of a belief that we're going to take the expectation over, and that gives us this expected utility. So there is a theorem which says that Bayesian Nash equilibria are possible if and only if there are Nash equilibria for the agent form. Now, if we have converted the game into this agent form, if we have converted all of those profiles, all of those things into this form, we have reduced it to just looking for a Nash equilibria overall. And
So, like,
that's
how do you get this equation? GI, this one that is
this one, right?
there. Yeah.
So what is happening here is each of these ti refers to an agent,
Okay. Yeah.
right? So now we are going to be looking at the utility for that particular agent.
Okay.
And to get any particular utility, we need to be, so I tells us which player's agent it is, and ti is basically telling us which particular type it is, right? So in the previous example that we saw, so we can think of player one who's trying to decide whether to fight or not. That's player one. Player two can either be strong or weak. You can think of that as two agents. Either it's a
Right.
agent who's strong or the other agent who's weak. Now, which one comes up and which expected utility comes up depends on which type you're at, or which particular player you got from this type versions, and hence you've just taken the conditional. That's it. If you look at it, this is pretty much what we had here also. Here we were talking about things in terms of behavioral strategies. Here we are talking about things in terms of, so far we're not talking about behavioral, we're just talking about pure strategies to begin with, actions.
Okay. So basically, we are taking an expectation over for one action sequence, and for t, we are multiplying this with the probability of t minus I given ti. Okay.
Okay. You can think of it as the belief of agent ti. Now that belief itself will be something that's conditional, because ti takes you to a certain part of the game, and ti is related to a type.
Right. Right. This is like a belief. Yeah, makes sense.
Okay.
Okay.
So there were two theorems in this week's lecture. Yeah. So first theorem said Bayesian Nash equilibria are the same as Nash equilibria for the agent form game, which means if you want to find the Bayesian Nash equilibria, you could convert the game into the agent form and then solve for the Nash equilibria, if that's the route that you want to take. That's one possibility. Another is Bayesian Nash equilibria are actually the same as Nash equilibria that you would get in any game in general also. This was proven in class. Anyway, we're not going to go through the proof. So now let's take a few examples and see what happens, whether we are able to find these Nash equilibria or Bayesian Nash equilibria. Okay, so right. Yeah, and now I have a few examples. Yes, examples where we'll be actually solving. Right, this is one example that I'll not solve. Reason is, this is actually a part of the assignments also. So if you already noticed, the assignments are asking you a question that was done in the tutorial, so I'll skip that. You can go through the lectures yourself. At least that'll be the work that you do on your own. What I'll do is, I'll just give you a brief of what is happening, more like describe steps and not worry about the numbers themselves. So here the example that we are given is, there are two players. There's player 1 has two types, and player 2 just has one type. So these are the payoff matrices for the two scenarios, with player 1's two different types. Player 2's type is fixed, so that's straightforward. And on top of that, we are given that there is a probability distribution on each of these type profiles, and that happens to be half. Now, to solve for any of these equilibria in these games, what we are ultimately doing is we are looking at we're solving for these quantities. We're solving for these quantities, but we don't have to worry about them, and we don't have to solve for them directly. What we can do is we can follow these kind of steps. So the idea here is, in this case, the way these payoff matrices are drawn is such that player 2 cannot distinguish between these two, meaning for him this and this is going to be one part. This is going to be in one information set, so it's going to be at the bottom and it will be one information set. Now if it is in one information set, that means for player 2 there are only two actions available. So actions for player 2 are just L and R. There are no other actions. There is no L, 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 R.
Right.
None of that is possible for him. That means whatever probability you assign here, that same probability you're going to have to assign for the other type also. So that becomes the first point. Then for player 2, for player 1 is where there is something interesting. So player 1 has two types, and since there are two types, he knows which type he's in. Knowing means those are two separate singleton information sets, meaning at each of them, whatever are the actions available, we have to take a Cartesian product of them. So that is all of them. So that means there is u1 d1 cross u2 d2. And since here we are talking about Bayesian equilibria, so what we are actually referring to are the behavioral strategies, meaning we're going to assign probabilities on this and this separately. Or in the matrix form, what we are basically saying is this part will have some probabilities. So we're saying P1 plays U1 with X and D1 with 1 minus X. And similarly for this we say Y and 1 minus Y.
Makes sense.
Yeah, if you understand this, then you'll be able to do the same process for no matter what these numbers are. Because here all of these things, deciding what to put where, is based on the informations. Who knows what? That's the core part. That's what you're using here. Okay, so now what is the process is, since player 1 has less number of strategies, it's better to start with player 1 and try to see if you can easily find a pure strategy Nash equilibria. Before even going to Bayesian, it's better to try pure strategy Nash, which means you can say, okay, let Q take some value, let Q be either 0 or 1. Take either of them. So you're focusing, okay, let's focus on L for example. So that is Q equal to 1. If you're focused on one of them, that means you've restricted your game to this part and this part.
Right.
Next step would be to see what would be the best response of player 2 to whatever has been fixed here. So if you fixed L here, what is the best response for player 1? What should player 1 do? Between 1 and 0, he would prefer 1. So here he would go for U1. And similarly here between 0 and 1, he would go for D2. So what happened is, we fixed a strategy for this and we found the best response for the other player. The key point is, we are doing it for the player which has less strategies, because that's the easier thing to start with. Okay, now that you know, okay, so we said, this is what we said, we got the best response. Now what we need to check is, for something to be Nash equilibria, the best response to Q0 should also be a best response itself. Okay, I didn't say that statement very properly. So if, so for example, in this particular case, I think we're dealing with u equal to 1 for the time being. So what we have here is, it's a b, no, not b, L comma u1 d1 situation. We know that for L, this is the best response. If we can find the other way around also, meaning that this is the best response for u1 d1, we are done. So that's the next step that they're checking. To do that checking, first thing you'll have to do is you'll have to find the expected payoff, or rather the payoff for this particular choice. Is there something else that can give you a better payoff than this? If there is, then for player 1, L is not the best response for u1 d1, and if that happens, then this is not something that's going to be useful. You'll not find Nash equilibria here, and you have to repeat that same process for q equal to 0 also. So this is like the first check. If you pass in this first step, you can stop right here, because you got something in Nash, pure Nash, then mixed Nash is by default there. You don't have to worry about it. But if you don't get something here, then you have to go to the next part. Now notice what we had was, player 1 had 2 strategies and player 2 overall had 4 strategies to randomize over. Not directly randomize over, but based on type we were randomizing. So now what you can do is, you can try and make sure, irrespective of the type. So now you're removing the type and you're just saying, in which scenario is it possible that the payoff for player 2 is the same no matter what this is, what pure strategy he plays. So we want the payoff for this overall, because we're considering both the types also, should match the payoff for this. Meaning this time what you're doing is, you are still taking q to be 0 and 1, and you're equating those to be equal. This is what we actually did when we were trying to find mixed strategies also. So what you do is, you'd look at this box or any one of these boxes and say, okay, what is the probability of getting this, whichever player you're talking about. So you're talking about player 2 here. So 0 happens with probability x times half. So actually that's 0, so not valuable. Then you'll look at this one. 3 happens with probability 1 minus x and 1 half. You're gonna keep adding on these terms. Similarly, you'll continue and you'll get these. And what that will do is, you have basically said what is the expected utility for a particular value of q. You've fixed that value to be 0 or 1 in this case. And you're just saying that this expected utility should match this expected utility irrespective of type now. And as soon as you do that, you will get some kind of a relation between these x's and y's, these x and y's.
Right.
And once you have a relation, you have managed to do a few things. You have some sort of a relation. You have whether q equal to 1 or q equal to 0 is useful. With this, you can try and identify, is there an appropriate value of q for which overall this can match. Like here we were matching the two sides and taking q value to be 0 or 1. Here you can then next try, okay, let's take q value to be something specific, and then see what do you get, and compare if whatever relation you got is still working for you or not. So in short, you're still doing Bayesian equilibria, but what you're starting with is to look for Nash. If you don't find that, that's when you go for all of these, and then the last step, this part, is just to confirm for will all the values of q have a Nash equilibria as long as this is satisfied, or is there a specific range or a specific value for which once this is satisfied we'll get a Bayesian Nash equilibria. So the overall process is a bit long, but I would strongly recommend that you go through this carefully from the videos. Okay?
Right.
Okay. So let's
So after this, like, in case it is not resolved, then we'll have to have those kind of conditions that if q is less than half and then greater than half and
Yeah,
then all those kind of things.
that's the part that will come here.
Okay.
So what you're going to be doing is exactly the same as here, but here what you did was you fixed q to be 0 or 1. So you were looking at pure strategies.
Mm.
In this part you're taking q to be something else, something some other value, whether that's going to be comparing half or half or whether that's going to be comparing something else is something that you'll see only when you start doing it. But overall you'll still be trying to equate those two sides, those two expected utilities.
Right.
Okay, so let's take a few examples to sort of get started. I'll start with very easy examples first and see if we reach slightly more complicated ones. Okay, so let's look at this. It would have been nice if I hadn't written this already. Okay, so this is an example with two agents. So there's player 1 and there's player 2. What are the types of player 1? He has just one type, so that's it, there's nothing there. Player 2 on the other hand has two types. In one scenario, let's say player 2 wishes to meet player 1, and the other scenario he wants to avoid meeting the other player.
Right.
Okay, so this type profile is I comma I2 1 and this is I comma I2 2. Okay, now actions are actually just b comma s for all players, so there's nothing in actions for all I and for all ti also. So also we are given this half, this half at the top means
The nature's probability of these two is half and half.
Okay, so for I made a mistake. Okay, now same thing, we are interested in trying to see can we find an equilibrium in this case. So to do that, first we need to assign those probabilities and we have to be careful with the information. So let's keep it the same way. We'll assign q for the player which has only which has less number of actions available. So for this case, player 1 is the one who can't distinguish. Right? For him, this and this is actually the same. Meaning whatever probability is assigned for b here, same probability will be assigned here also. And whatever is assigned here will be assigned here also. That means we can to keep similar notation as before. So keeping q here. So q is here. This is 1 minus q. Okay. So to write more carefully, what we have done is for player 1, the choices he has are just b and s. For player 2, he actually has two types, right? He has some type here and some other type also. The actions might still be the same, that is true, but there are two types. That means the total number of strategies available that are to be randomized over are quite a few, and we are randomizing with respect to each of those types. So that means we will assign probabilities here and here. So that becomes okay, let's call this x, this 1 minus x, this y, and this 1 minus y.
Yeah.
Okay, so just now, just like before, what we're going to do is we're going to try and see, does it help if we take a pure strategy for one player? If one player plays something, is there like a best response we can find for the other player and all of that kind of arguments? So let's make a
Right.
table to talk about best responses. Okay, so let's take q equal to okay, let's start with
1.
q equal to 1, meaning we are dealing with b. If player 1 decides to
So
play
B.
b, what should player 2 do? Player 2 needs to pick something over here, so he needs to make a choice between b and s here, and he needs to make a choice here, so he has two things to choose from, two parts he has to make choices in. So what would player 2 do?
Okay, so if you was equal to 1, then player 2 would choose B
So how did you
in
choose
first
that?
case
You just
and
compared.
S in second case.
Yeah, 1 second. So when you said player 2 would prefer playing 2, he's just comparing the utilities. He doesn't even have to look at anything expected here.
Yes.
So then player 2 would play b in the meeting case, and what would he play in the other case?
S.
Yeah, he would play s here. So we did the first step. This is like starting of the first step rather. So we know that this is player 2's best response to player 1 playing b. So this is very rough notation. If you want, you can clean up the notation and then do it more carefully. So now next step that we're supposed to do is we need to look at the expected payoff and then compare that with is this player 1 playing b the best response if player 2 had played this? That's the next thing that we want to answer. So let's first calculate the
Yes.
expected payoff. So when I'm calculating expected payoff, I am calculating it for this action profile. This is my action profile. This is player 1's action. This is player 2's action in the two types. Okay, so this is u1, this is u1 for t1, this is u2 for t2. Okay, so what is the expected utility here? Now if we're talking about expected utility, we're basically going to have to compare this is, by the way, whose expected utility do we need? Player 1's or player 2's?
So we want to check if B is the best response to B, S, so we can check for player 1.
Correct. Since this part of the argument is already finished, we already compared utilities as much as we needed. For the next part of the argument, we are looking at player 1 again. So it's player 1's expected utility that we want. So
Why player 1? Because he started.
not like he started, we have this much argument complete, that player 1 chose something and player 2 has a best response to that. Now we want to verify if for this strategy of player 2 is b a best response for player 1 or not. So to do that, what we would have to do is compare this payoff with whatever other option payoff player 1 has.
Okay.
But the comparison is to be done by player 1 because he wants to know if the best response to this by player 2 is actually b or not.
Okay.
Yeah, I can't think of a simpler way of saying this. Okay, so to do that, so this is b, so we look at 2 here, This is type 1. So we did BB. Now we do BS, which gives us 0. And that is to be taken with probability 0. This gives us 1. Okay.
Right.
Now, next thing for us to continue the comparison would be, we've already seen what happens if player 1 plays B. Right? If we want to compare it with if player 1 does not play B, so let's say it plays the other action, so S, B, S. What's the expected payoff in this case?
Like, can we do this way that, like, let's say we take P2 second part S, and then we just see that which one is better in P1 in that case?
As long as the expected utility is fine, it's okay. Because this is
Okay.
the one that needs to be better.
Okay, the total value.
Yeah,
Basically.
see,
So
player
it will
1
be individual.
Player 1 is the problematic one here, right? Player 1 doesn't know which type it is, so he needs to take expectations. And that's it. For player 2, it's easy. Player 2, you're directly comparing. That's why this comparison was straightforward.
Yeah, that's right. But what I'm saying is that, let's say we calculated B comma S. Now, can we do this way that, like, we put
What
so
is B
let's say we
comma
are
S? Because
B comma S P2's response, best response.
okay.
So now let's say in the first box we pick B, and then we check that for P1 B is better or S is better, and then we can verify that B is better. So that is verified, and then for the second box. Yeah. I mean, my question was just that, do we need to calculate the expected payoff, or
It's
can we do
safer to calculate the expected
calculate
payoff.
the
Yeah.
Okay.
Especially for the player who doesn't know the forms, doesn't know the types.
Okay,
It's
so you'll
safer to do
calculate the payoff for both B and S and then compare.
Yeah.
Okay.
So for S, it will be okay. So for S, it is 0, 0 with half and 1 with half. So that's clearly less. This is P1's expected payoff for this strategy. So what actually happened in this process is B was the best response. Best response was denoted by R, right? R2 of once again. I don't recall what was the notation for best response. Okay, anyway, so I am going to denote it this way. So let's say best response of player 2 towards B, meaning player 1's action, includes this B comma S. This is player 2's, and player 1's best response against B comma S, this is player 2's again, actually is B itself. And because this happened, there's a cross thing that's happening between best responses. That means this is actually a Nash equilibrium. So what we get is B comma S. This is a Nash.
Okay, makes sense.
Yeah. So
then this way is actually better and correct, because if we would have done in the way that I said, then it would have come out wrong.
Oh,
Because
is it?
for, I think, yeah, because for the second box, if we take the P2 strategy as S, then for player 1, S is the better response. So that way.
See, for player 1, you can't make that decision without looking at the expected utility. If this value was not half and half, then things would have changed. Right? So it's better, it's safer to just look at the expected utilities.
Right.
Expectation is with respect to the different types, because you don't know the types.
Right.
Okay, so here what I did was I actually knew which was the correct response, and I did only that. If you don't know, what you can do is you can take the strategy of each player. This is the general process that you can follow. So you can take the strategy of player 1, those are B and S, and then see what is the best response to B. So best response of player 2 to this strategy, whatever that is, that will be a pair coming here and something coming here, and repeat that same but for player 2 now. So player 2 would have whatever his options and the best response to that. If there is a match, then that's going to be a Nash equilibrium.
Right.
If that doesn't happen, then we have to go to the next step also. Okay, this is best response. I keep changing my notation, right?
Even I can't remember what was the.
Yeah. That's what, if you look at these tutorial notes, you might not recall what was done in these sessions. This is best response. Okay, so this was an easy example. I think I have one more easy example. Yeah, this is again an easy example. So let's say we take one particular version of alpha, whether we take it to be less than half, more than half, equal to half, whatever, but we take something and then do the rest of the arguments, because otherwise it becomes a little annoying.
Okay.
Okay,
We'll choose the value and something.
now we can do either of them, I don't mind. This is just to verify that this is what you will get if you tried any other forms. We'll just do one of them now. You can try the others later on if you want.
Yeah.
Okay, let's do half, less than half only. Okay, so same arguments as before. We first start by talking about the types. Player 1's type, there's just one type. Player 2 has two types. Strong and weak. And accordingly their action, the set of actions would also be different. So for U1 it's just to choose between fight and yield. U2 chooses with respect to the type for his profile, so that's T1 or T2. Both of those choose from the same thing, F, Y. So pretty much the same thing as before. The only thing that has changed here is the numbers, that's all.
Okay.
Actually, let's do this. Let's F, Y. Oh, that's the same answer as before also. Okay, let's do this one. At least there'll be some effort we'll have to put in to get to that value.
Then how do you figure out just by looking what will be the Nash equilibrium? How do you figure out just by looking what will be the Nash equilibrium?
No,
You
you
just
can't.
did, right?
You can't figure out. No.
Okay.
This is just to sort of make the question a little easy for you. Ki, like, show this that for certain values of alpha, this is what Nash equilibrium you will get. If you have to do it completely on your own, then you'll have to go through all best responses for each player and then find if that's where you're going to get from.
Yeah.
Okay, same logic as before. So I'm just gonna plug the values. This is what I'm taking as Q and minus Q. Player 1 can't distinguish between these two, meaning for him the options F and Y would have the same probability here and here. So this is Q, this is 1 minus Q. Player 2 on the other hand, this player can distinguish between these two types of the game. Hence, the probabilities can be different in the two parts.
Right.
Okay. So, in short, what I've written is the behavioral strategies only. For player 1, there was nothing really, but for player 2, there's a proper behavioral strategy. Okay, so let's do the same arguments as before. Let's take Q to be 1. So the order of arguments is same. We have chosen a strategy for player 1. So we now see what is the best response of player 2 for that strategy. So what would player 2 do? Player 2 is supposed to choose between 1 and 0. So here he'll
Yes.
choose to fight. What
Yeah.
will he choose to do here?
Yield.
Yeah. So for player 2, the best response is fight, comma, yield for strong and weak. Now, the next thing for us to do is to calculate the payoff. Whose payoff are we going to do?
P1.
Exactly, P1's expected payoff. And the expectation is with respect to alpha. So there's alpha times something, and then there's 1 minus alpha times something. And we're doing it for this profile. So Q equal to 1 is F. Okay. So player 1, it is minus 1 here and 1 here. That gives us 1 minus 2 alpha. Correct.
Can you just go up in the diagrams?
Yeah.
So for alpha, it is -1, and for okay, it is 1. Yeah. Wherever Q is 1 is where we'll be taking, right? Okay, got it.
So now we will do the same thing, but for the other option for player 1, which is y fy. So for y fy, it is alpha times 0. Oh, that is just 0, is it? Okay.
Okay.
But recall what we have taken. We have taken alpha to be greater than half. Right. So this is actually going to be a negative quantity. Yeah, that's why it mattered. Okay. So that means F is the best response to. Oh no, sorry. Y is the best response to Fy. But that broke our chain.
Yeah.
So that means this is not enough. So now what we need to do is see. So this much is done. All we need, all that is remaining is if Q was taken to be 0 or that he played Y. In that case, would the best response be Fy for player 2? This is all that we need to verify. If we can verify this, we're done. So, okay. So, the verification is with respect to player 2 now. We are fixed in this portion.
Just automatically, like this in the question when it says to show Nash equilibrium is y, comma f, comma f, this automatically means that it is a pure strategy, right?
Yeah.
Okay.
Because it's written without any probabilities, right? They've just given you the actions themselves.
right?
So you can see that already here. If player 1 played Y,
Hmm.
he would choose, player 2 would choose F here, and in fact F here also.
Right.
Right, so, okay, so this is not it. This is not it. Player 2 goes for, this is first version. First version did not give us a Nash. This is the second version. The continuation also is not working, but okay. Player 2's best response to Y is F comma F. Now to repeat the whole thing, so F will calculate the expected payoff for Y comma F comma F. So
Right.
what would that be? That's just 0.
Hmm.
Okay, so this is 0. If it is player 1, the only thing that he can change is it can go from Y to F. So let's see what happens if he was going for F. Then what is the expected payoff? It's comparing this with this.
Minus alpha plus 1 minus alpha.
So this gives us
1 minus 2 alpha.
correct. 1 minus 2 alpha. And since we are in the region where alpha is greater than half, that means this is the best response for player 1. So in short, what happened here is which one was it? Okay, Y comma F is the Nash equilibrium, because this was the best response to Y and Y was the best response to this. So whatever
sense.
those players were playing, that is the best response.
Got it.
Now there is one more way of doing the same thing. I'll not actually do it, but I'll tell you the idea, because we have created a lot of the details that we would need to do that. That is the agent form. So what you could do is, instead of writing where are the strategies? Instead of writing the strategies as F comma Y, you could write them in this way. So F comma F. And create the table with expected utilities. Now, if you're writing F comma F, then the expectation is with respect to what? The types. Right? And here you can have F comma whatever it was, Y. Fill out this whole table and then search for the Nash equilibrium. That's also something that you can do. And doing it this way is similar to sort of doing it in the agent form, but how you write the expected utilities, you have to be careful about that. Meaning, okay, we have some of the expected utility values here only. So see, we calculated for this one, that is 1 minus 2 alpha, for Y comma FF.
0.
This is 0. Then I think we have a few more. Y comma Fy, Y comma Fy. This is also 0. Okay. This is some of the values, and you can fill out the rest of the values and search for a Nash equilibrium. And since we know what alpha we're dealing with, we can easily figure this out. Okay. 1 minute. Okay, I'll quickly talk about what was it? Yeah, I'll quickly talk about a Stackelberg game and then try to do an example similar to what was done in tutorial. All I'm going to do is just change the numbers in any of these so that the best responses don't work anymore. That's all.
Okay.
Just a moment though.
Sure.
By the way, I have kept an extra class before your last tutorial. So consider this as sort of an announcement to bring questions if you have any. Otherwise, I'll quickly take a recap of the kind of problems that we've solved so far and if you have any doubts while we're going through it.
Which date would that be?
I do not recall, but you should get an email from them at some point.
Okay, sure.
One second.
So before the last tutorial, you mean that we'll have a session next week, and then the last session will be next to next week. So before
Yes.
that, you'll have another session.
I think I chose a Saturday.
Okay.
Yeah, I don't remember the date.
Not the Saturday, though, right?
On 11th. So that there is time.
Oh.
Not this Saturday, next Saturday. We
Okay,
have
okay.
2 more sessions remaining. This is 10, so 11 and 12. Before 12, 2 days before 12, 2 or 3 days before 12 is when this session is kept.
Okay.
Let me know if you get an email for it or not.
Sure.
Okay. Yeah. So where were we? Okay, let's quickly go through Stackelberg equilibrium and then let's see if we can take another example to get a bit more comfortable with all of this. So far the kind of equilibria that we've talked about are the ones where both the players are not making any commitments. They are just taking actions based on whatever type or whatever information that they get. While in Stackelberg equilibrium games, there is one player who says the strategy that he's going to play and he announces it. So it's not that he has fixed his strategy, he's also making it public. So all the other players know what he's going to do. So the word that is actually used is that he commits first. And what he's committing to is not an action, not just an action, but a strategy. And once he has committed to something, he makes it known to the follower. So a simple example of this could be like the security strategies that we have, the kind of protocols that we have to follow. For example, when we enter an airport, we know those rules. So we can think of the ones who make the policy or who come up with those security rules as the leader. Then based on whatever rules they made, we know those rules, and then as the other part of the player, meaning the followers, we take our own actions from the set of actions that we do have available. So now the difference here would be the follower would not be making a random action. He will, whatever action he takes, he'll take an action or he'll choose his strategy based on the leader's strategy. In fact, what he will do will be the best response to leaders. So okay, this is the notation. Okay.
So a leader will commit and obviously follow through, right?
So now what happened here is, if the follower has only one best response to something that was, some strategy that was chosen by the leader, then the leader will actually be keeping that in mind, that okay, this is the process, this is how the follower is going to go about it. So whatever strategy that I am committing to and announcing, it will be something that satisfies his own objectives, whatever those objectives may be. So if we were to write it slightly more formally, so the utilities would be, this is the utility for player 1, the leader, and these are the strategies for both of them. This is the utility for the other player. So now what the rule the rule here is, gamma 1 will be decided first. Leader will come up with his own strategy and he'll announce that strategy. Now whatever may be that form of announcement, but it will be something that will become available to the follower. Then the follower will just take a best response with respect to that strategy, and best response means keeping this fixed, whatever are the best strategies that he can play, such that he gets as good as a cost he can. Whatever minimizes his cost, that's what he'll go for. So now if we were to write down what would be actually the cost of player 1, it would be, okay, there are two cases. So right, if the best response has only one strategy, that means player 2 only can choose one strategy from this set, this set is a singleton, then player 1's job is very simple. All that player 1 has to do is take the best response of gamma 1, take gamma 1 itself. So now he has a function that pretty much depends on gamma 1 and has no dependence on gamma 2, that just got erased, and just take the argument of that. If he takes the argument of that, what he gets will be the strategy he should choose. And this process, or the equilibria that we get out of this gamma 1 star and gamma 2 dash profile that we get, will be called as a Stackelberg equilibrium. So here there is an order. One plays first, second player gets to see what the first player played and is just choosing a best response to that. And that best response will be, if that best response is such that there's just one best response, meaning this is actually like a function, this gives you a singleton thing, the set gives you something singleton, then you can just take an argument over this. The problem arises if this set is not a singleton. Then that means for any given gamma 1, the best response actually has a lot of different options, and player 2 now needs to pick one of those at random. And based on what he picked randomly, gamma 1 or player 1 needs to decide how should he play the game. He can no longer just take an argument here, because there is not one option but many. So there are two attitudes or two ways the leader can go about it. The leader can say, okay, from the set of these options, what I'll do is I'll choose the one that gives me the best case scenario, which is if I'm taking the gamma 2 that minimizes this. So he's assuming that player 1 is optimizing this quantity with respect to gamma 2. He takes that quantity, but player 1 is doing for J1, player 2 actually has done it for J2. So he's taking that same thing, but he's taking the argument with respect to J1. Now once he has done this, he's being optimistic here that player 1 would have chosen, whatever player 1 has chosen is actually the best that could have been there, and then just takes the argument of that and hence gets gamma 1 star. The other is to sort of take the extreme route and say, okay, this is like assuming the other player, this is like either a zero-sum game or a completely opposite behavior, that player 2 would want to behave in a very negative way, and hence player 1 needs to take care of that and remove that scenario. So he takes the maximum from there and deals with sort of like the worst case scenario and takes the argument with respect to gamma 1 here. and that's what gives him his strategy. This is all if we are assuming that there are 2 players only. So this is with 2 players, 1 follower, 1 leader. Now that's not necessarily always the case, right? There could be 1 leader and n number of followers. Then this can be thought of as, let these n players find an outcome from their own set of rules, meaning let the game play out between these n players and have a Nash equilibria come out of here, whatever kind that is possible. And then player 1 would just look at that Nash equilibria and just minimize this quantity J1 of gamma 1, whatever is the Nash equilibria done by all the players. So let's just call it gamma. And he'll just try and minimize this quantity. If there's only 1 Nash equilibria, same thing, it's simple and easy to do. If there's more than 1, then the same idea happens again. You have to look at optimistic and pessimistic leader and so on. Okay, I'll take an example of this. Not a concrete example, but at least the idea of it. So for example, let's say the leader is the one deciding or designing the roadway system. And the n followers are just the drivers who either take that route or take that route. So maybe there is a route like this. Okay, so this is the starting point, this is the ending point. This is the current scenario. So this takes, and let's say there are total n drivers at any given point of time. You can minimize it to be just 2 and then also think about it. And suppose we are given how much time it takes on each route. So how much time it takes on this route and how much time it takes on the other route. So let's say this one is n by 2 and this one is some quantity minus n by 2. It doesn't matter what those numbers are. The point is there is some utility. So what will happen is, this is still at the level, this is the game available to the drivers, so the n followers. Now the leader is now deciding, if I add a route in between with, say, which takes some time t, what will happen to the distribution of how the traffic moves in the 3 different lanes, and ultimately would it help to add that particular road or not? So meaning, if suppose by default this road has much less traffic, so this is just taking the fourth of the value, or this takes very less time as compared to the other ones. By comparison, without even thinking too much, this road is clearly better than this one. The comparison of these two depends on what is the number of followers. So if overall this route is better, then most of the drivers would end up taking this route, and hence the overall time on this route for each of those player would still be higher as compared to some smart player who decides, you know what, I'm not going to take this route even now and rather take this route, because here the number of players actually on this route would be less, because optimally this is the better choice for all of them. So adding a road might increase traffic in that road and deviate from the other two, making these two completely free, and hence the objective of adding a road and distributing the traffic sort of went away. So thinking whether to add and how much the time should be reduced and what happens, this can be thought of as the designer's part or the leader's part, and hence whatever the followers do, that can be thought of a simple outcome of the game, or some kind of a Nash equilibria, or whatever equilibria comes out of that game.
Good, makes sense.
Yeah. Okay, pretty much out of time, right? Okay, so let me just go through this example only then. So remember, in the other examples that we saw, we were basically looking at this portion and we found a Nash equilibria here itself. But that may not always be the case, meaning just by comparing pure strategies for q equal to 1 or q equal to 0, we were able to find mutual best responses, and hence that became our Nash equilibria. That may not always happen, and hence this part is important. So I would recommend go through this. If you still have a doubt, maybe we can take it in the next lecture, and maybe we can spend like 5-10 minutes in the beginning itself.
Sure.
Okay, so with this, at least I've covered whatever I planned. So today we talked about games with incomplete information, meaning players have type. Players having type is like saying some players, for example, in this example, player 1 will know what type he has. Maybe he's strong or weak, but the other player wouldn't know the type of player 1. And this kind of scenario can be captured in an imperfect information game, including one nature player or a zero player who assigns probability for each of these types, or these are sometimes also called as chance moves, these ones. Then we looked at quite a few examples of what does it mean to have a type, and then we finally looked at how to compare the Nash equilibria in the two scenarios. If we are dealing with Nash equilibria itself, the core one, it's before we got to see any type, so we're just saying unilateral deviations will not help in behavioral strategies. And if we are looking at Bayesian, then we are looking at the expected utilities conditional on the type of each player. So player i's type is ti, so conditional on all of those types. If unilateral deviations don't help, then what we get is a Bayesian Nash equilibrium. And we stated these theorems which compared Bayesian Nash equilibria with Nash equilibria itself, and also that we can think of these Bayesian games in terms of agent form, or each of those branches that come out from nature can be thought of as a different agent, and we can denote that agent by ti to remember which player it is a part of and which part of the game it is going towards, or which type it is going towards. And in that case, the expected utility is just the same as what we would have gotten from Bayesian equilibrium itself. The only difference in this form is that we are writing it for an action, not a behavior, not a behavioral strategy. Same thing could have been written for a behavioral strategy as well. And this theorem says Bayesian Nash equilibrias are the same as Nash equilibrias of the agent form game. So you can also solve for Nash equilibria of these Bayesian games by looking at the agent form. And we saw a few examples, at least a few easy examples of how to go about it. Yeah, with this I've covered everything. Any questions?
Nope, nothing on week 10.
Okay, perfect.
There was one question I had related to the exam though. So like regarding in the exam, like we'll have multiple choice questions and we'll have single answer type questions. Will we have any kind of theoretical question also in which we have to explain things or like no or
Whatever will be in the form of MCQs or numerical answers. That's about it. No explanations, no subjective questions, in short.
Right.
Okay, yeah, Vivek, you had a question?
No, thank you.
Okay, perfect. So let's end here. Thank you so much. Bye bye.
Thank you so
Bye.
much. Thanks a lot. Yeah. Okay. Bye.